Okay, I'm going to go over the PES practice and the calculations. I'm really just going to do the PES practice. We'll handle calculations in a different video. I'm at school and the air is on, so that's the noise you hear, and I apologize for that. Really can't do anything else about that. I'll try to make this as quick as possible with you still being able to get the information that you need. Let me back up. If you don't have a periodic table in front of you, go get one. You need that so you can account for your electron configuration. All right, so question 1, which element could be represented by the complete PES spectrum below? With every single photoelectron spectrum, if I were you, I would write down the electron configuration above the peaks so that you know what you're looking at, especially in a more complex question where you have to compare two things. Okay. All right, so I have the 1s2 peak, the 2s2 peak, and the 2p3 peak. And I know this is 3 because each one of these lines within the peak represents a half of an electron, or better stated, a pair of lines represents 2 electrons. So that's 1, 2, and then this is 1, 2, and then 3 electrons. Okay, so this is going to be nitrogen. Nitrogen's electron configuration ends in 2p3. The other thing I want to point out is make sure you understand that when you have this large gap in energy where you go from a very high bonding energy to not quite as high of a binding energy, that's due to moving to a different principal energy level. And principal energy levels are the energy levels within an atom. So principal energy level just means I'm moving further and further away from the nucleus. All right, next questions. Which of the following best explains the relative positioning and intensity of the 2s peaks in the following spectra? So you have lithium with 3 protons, and then you have beryllium with 4 protons. So you're looking at just the 2s peaks. So lithium would be 2s2, lithium would be 2s1, beryllium is going to be 2s2. So you're looking at the same energy level and the same type of orbital. Therefore, the shielding or the distance from the nucleus is not going to be a factor when you're comparing these. What will be a factor is the Coulombic attraction based on the nuclear charge. So since lithium has more protons than beryllium does, its nucleus is more attractive. So beryllium has a greater nuclear charge than lithium. Therefore, it will attract its electrons better than lithium is able to attract its electrons in the same energy level and same orbital. Okay, and as a result, the 2s electrons in beryllium will have a greater binding energy than the 2s electron in lithium. So answer choice A is your answer. Okay, next question. Given the photoelectron spectra for phosphorus and sulfur, which of the following best explains why the 2p peak for sulfur is further to the left than the 2p peak for phosphorus, but the 3p peak for sulfur is further to the right than the 3p peak for phosphorus? You've got to label your spectra, so those are labeled for you there. And then the other thing you need to look at is, what am I specifically being asked about? So I'm being asked about the I'm being asked about the 2p peak, and I underlined the wrong thing. Sorry about that. 2p here and 2p here. Okay. Why does sulfur have a greater binding energy and phosphorus has a lower binding energy? Well, sulfur has 16 protons, phosphorus only has 15. So the fact that I'm in the same energy level, same type of orbital, sulfur has more protons, so its binding energy will be greater than that of phosphorus. But then I go out here to 3p for phosphorus and 3p for sulfur, and this helps when you write down your electron configuration. So phosphorus has a 3p3 electron configuration. So each of these 3p electrons is in an orbital by itself. Sulfur, though, ends in 3p4. So this 3p peak represents 4 electrons. So one of those electrons has to double up, okay, right here. And when you have 2 electrons that occupy the same orbital, that increases electron-electron repulsion. And as a result, it makes the binding energy for this electron right here not as great, because if this electron right here could be removed, that reduces the electron-electron repulsions, okay? So since the binding energy for this electron is not as great, the peak for 3p for sulfur will not have as high of a binding energy as the 3p peak for phosphorus, okay? So the answer here is A. Sulfur has a greater effective nuclear charge than phosphorus. Yes, it does. It's got more protons. So that explains my 2p. And the 3p sublevel in S has greater electron repulsions than phosphorus. Yes, it does. That explains the fact that my 3p peak is further to the right for sulfur and not as far to the right for phosphorus. This slide explains what I just did. So in a group 6 element such as oxygen, 2s2, 2p4, has a smaller ionization energy than the preceding group 5 nitrogen element with 2s2, 2p3. So as a result of repulsion, it's easier to remove an electron from the doubly occupied 2p orbital of the group 16 element than from a singly occupied p orbital of the preceding group 5 element. You need to look for, if you're given a question about this, look for elements that are in group 15 and group 16. Group 15 elements, their electron configurations end in energy level P3. Group 16, their electron configurations end in energy level P4. So right there where you have that doubling up, that increases repulsion. And to decrease the repulsion, the ionization energy for that paired electron becomes lower. Okay, so just kind of keep that in mind. They could give you phosphorus and sulfur, or nitrogen and oxygen. Those are the ones that they'll probably pick the most. All right, next question. Looking at the spectra for sodium and potassium above, which of the following would best explain the difference in the binding energy for the 3s electrons? Well, potassium has 19 protons, sodium only has 11. So I'm looking at the same energy level, same orbital, but potassium has a greater nuclear charge, so it'll attract its 3s electrons stronger than sodium will attract its 3s electron. Okay, so answer A is 4. All right, answer 5. Looking at the spectra for sodium, potassium, and above, now you're going to write an explanation that delineates the difference in signal intensity for the 3s electrons. So signal intensity tells you the height of the peak. It means how many electrons with a given binding energy were present. The more electrons that you have with a specific binding energy, the greater the intensity will be for that peak, and the higher the peak will be. They want to say, why is the potassium 3s peak higher than the sodium 3s peak? And the reason is because potassium has 2 electrons present in 3s, and sodium only has 1 electron present.
Miss Marilyn, could you please report to the front office for your keys?
Sorry about that. Like I said, I'm at school. Okay. This question in class was difficult. So you're supposed to explain, or using the statements, which explains the position of the peaks. So if you'll look, oxygen and carbon are both displayed with their 1s peak. titanium has a 2p peak. So right away you should know that oxygen has 8 protons, carbon has 6, titanium has 22. So titanium has the greater nuclear charge. But in this particular PES, you're not looking at the 1s peak for titanium. You're looking at the 2p peak for titanium. So the 2p peak is in the second energy level, which is already farther away from the nucleus. So its binding energy is not as great. So that explains why titanium, why its peak is right here in the middle. And then oxygen has a higher nuclear charge compared to carbon. So it will have a peak further to the left, a higher binding energy in 1s than carbon does. Okay? And then titanium will be in the middle. So the answer here is D. Titanium has a greater nuclear charge. Yes, it does. But the 2p sublevel experiences greater shielding than the 1s sublevel. That means that there's more stuff in between the nucleus and the 2p sublevel that kind of protects that 2p, or the 2p electrons from being attracted to the nucleus. So the binding energy is a little bit lower. Shielding means protection from the nucleus by a complete energy level prior to where you are. So the first energy level of titanium shields the second energy level from the nucleus somewhat. All right, so in this PES, you're supposed to explain why scandium most commonly makes a +3 ion as opposed to a +2 ion. First, you need to know that plus means you lose electrons. Minus, if this were to form minus ions, it would mean that you gain electrons. So if you label your PES diagram like I've done up here, what you'll see is that technically...
Ms. Marlowe, would you please call the front office? Ms. Marlowe?
Sorry. You'll see that the 3D sublevel is in the third principal energy level, but it's so high in the third principal energy level that it's very close in energy to the 4s2 electrons. So in class today we talked about how if you have a transition metal and you're going to make an ion, first you'll remove electrons from the highest principal energy level, s and p orbitals. So the highest principal energy level that I have here is energy level 4. Okay, so I'm going to take out both of those electrons first. And then because the D sublevel is so close in its binding energy to the 4s sublevel, I'll remove this D1 electron next. So because those binding energies are so close, it's likely that if you have enough ionization energy to remove the 4s2 electrons, you'll then also remove the 3d1 electron. Okay, so the answer here is the amount of energy required to remove an electron from the 3d sublevel is close to that of the 4s sublevel. But you wouldn't go down to the 3p sublevel because that represents a tremendous gap in energy. So the energy to remove the 3d electron is much less compared to removing the 3p electrons. All right, in terms of electron configurations for ions, in general, if you want to write electron configurations for ions and you want to remove electrons, then you'll do it in the reverse order that you wrote the configuration. So if you write sodium's 1s2, 2s2, 2p6, 3s1, you would remove first from the last thing you wrote, the 3s1. And that's true for your elements except for transition metals. With transition metals, when you make those positive ions, electrons are removed from the valence shell, so that means the highest principal energy level, valence shell s orbitals, before they can be removed from the valence d orbitals when you have a transition metal. So cobalt has the electron configuration argon, that's its core, 4s2, 3d7. If this were not a transition metal, then I would remove first from this 3d7. But since it is a transition metal, I actually remove first from the 4s2, and then I dip back and remove from the 3d sublevel. So cobalt can make +2 ions where you remove where you remove the 4s2 electrons, or it can make +3 ions where you remove the 4s2 electrons plus one of the electrons in the 3d sublevel. So just know that when you have a transition metal, you'll remove your highest energy level s electrons first, then you'll dip back down to the 3d. Alright, on the photoelectron spectrum for magnesium given above, draw the spectrum for aluminum. So I have here the electron configuration for magnesium and as well as for aluminum. So aluminum's peaks are going to be further to the left than magnesium's peaks because aluminum has a atomic nuclear charge of 13 protons, whereas magnesium only has 12 protons. So the nuclear charge is greater in aluminum than it is in magnesium. The greater the nuclear charge, the higher the binding energy at each peak. Okay. Second thing, magnesium's electron configuration ends at 3s2. So this peak right here would be the last that you would write for magnesium. Whereas aluminum has one more sublevel. It has the 3p sublevel, and it's got one electron there. And we talked about in class today, when you have s, p, and d sublevels on the same energy level, the d sublevels are at a higher energy, and therefore less ionization energy is needed to remove the d orbital electrons. Then next, the p sublevel is an intermediate energy level, and the s sublevel is the lowest energy sublevel. So I'm not dealing with d here, I'm just dealing with 3s and 3p. It would be easier, less energy would be required to remove this 3p electron than it would to remove the 3s electron for aluminum. So that's why the 3p electron is further to the right, lower binding energy, than the 3s electron. Okay, I tried to explain this in class. At this point in the video, if you want to stop, you can stop me. An orbital is a region within the electron cloud where you have a 90% probability of finding an electron. And so you can show that through density graphs like this one, or you can show it through radial probability curves or distribution curves. So this point right here, at a distance of about 50 picometers, that's 10 to the minus 12 meters from the nucleus, would be where you're most likely to find electrons in a 1s orbital. And if you were to plot a 1s orbital, a 2s orbital, and a 3s orbital, you'd get three different radial probability curves. Okay, the 1s orbital, if you took the average of the distances, right here along this blue line would be where you're most likely to find an electron in the 1s orbital. If you did the same thing for 2s, right here, a little further out from the nucleus, you would okay, I'm sorry. Let me start over. All right, so in your 1s orbital, this blue line would be on average where you would find most or where you would most likely find the 1s electron. This blue line here would be where you'd most likely to find the 2s electron. It's a little further out from the nucleus. And then the 3s right here would be where you'd be most likely to find your 3s electron. Okay? And so each time you go up a principal energy level, the distance from the nucleus increases a little bit. Okay? But what's interesting is this hump right here, and then these two little humps right here and right here on the 2s and 3s radial probabilities respectively. Okay? And you can see that here. So what happens is the s orbital is the smallest orbital. P's are larger and D's are larger than that. F's are the largest, but we're not really going to deal with F. So that means that a 2s orbital is farther from the nucleus than a 1s, but the 2s orbital, because it's small, it can kind of invade the space of a 1s orbital, and that's called orbital penetration. So that 2s orbital can kind of sneak and get close to the nucleus for a small portion of time. The 3s can do the same thing, and it can also penetrate the 2s orbital. Okay? So when this penetration happens, what it does is it decreases the energy of the 2s orbital and the 3s orbital, and so it makes that 2s orbital and that 3s orbital more attractive to the nucleus compared to if this penetration did not occur. The p sublevel, its orbital is larger, so it cannot do this penetration, and D's even bigger, so it definitely can't penetrate. So I did the example in class. If you're standing in a crowd and you have a dog or a cat, a small dog or a small cat, or a small child, because that creature you have with you is small, if they get down, they can weave their way through a crowd. Whereas you're tall and you're going to have to, meander around people, and you're going to say, excuse me, it's going to be harder for you to get around. And so you're not as able to penetrate the crowd as well as a small creature. And your s orbital is a small creature. It can penetrate lower energy level orbitals, which makes that s orbital more attractive to the nucleus. So in this picture, or in this radial diagram right here, this is your 1s, the red is your 2s, and the purple is your 2p. What I do not want you to say is that the 2s orbital is closer to the nucleus than the 2p orbital. It's not. The 2s orbital is actually a little bit farther away from the nucleus than the 2p orbital, but the 2s orbital can penetrate closer to the nucleus. And when it penetrates closer to the nucleus, that means there's greater nuclear attraction, and it makes it more difficult to remove electrons from the 2s orbital compared to the 2p orbital. And this is true for any energy level that you're in. So if I'm comparing 3s and 3p, or 4s and 4p, or 5s and 5p, the same thing happens. That s orbital can sneak in and penetrate a lower energy level s orbital. So it kind of zaps the energy that's there and makes that electron more attractive to the nucleus. Okay, that's the end of that. So I hope that didn't confuse you too much. All right, I'm going to pause here, and then I'm going to start another video.